Hi everybody and welcome back to our final discussion of Unit 1 over Chapter 5, Energy Expenditure, Fatigue, and Muscle Soreness. I apologize, this chapter is kind of the catch-all chapter, so this one's going to be a long one. So to start, we need to talk about how do we actually measure energy expenditure. We have two ways that we do this. The first is direct calorimetry and the other is indirect calorimetry. So direct calorimetry is where we are actually going to directly measure the calories that are burned by an individual. This is going to give us an idea of substrate metabolism efficiency. We know about 40% of the substrate energy that is produced gets to be used towards ATP, and then about 60% of it is lost in the form of heat. So the human body, in terms of an engine, is very inefficient. We also know that heat production will increase with energy production. So we can measure this directly with calorimeter. We do this through a very fancy literal room where we run some water through some walls, and then we are going to use the body temperature to increase the water temperature. So a direct calorimetry actually looks like this. So when people do direct calorimetry studies, they actually live in this room, they eat in this room, they exercise in this room. So the pros of using direct calorimetry is it is incredibly accurate, and it's really good for giving us rusty metabolic measurements. However, as you could probably guess, having an entire room dedicated to just measuring somebody's body temperature is incredibly expensive. Also, to get really accurate results, you have to do this for days at a time, so you're kind of holding your subjects hostage. So it's very slow. Also, we have some issues with heat being added by any exercise equipment. We can also have some measurement errors from sweat, and it's not really practical nor accurate for exercise. So realistically, we tend to use direct calorimetry more for nutrition studies than exercise studies. This means that in exercise studies and physical activity studies, we tend to use indirect calorimetry. This means we're going to estimate the total body energy used as opposed to directly measuring it. And we do this based on oxygen used and CO2 produced. We do this by measuring respiratory gas concentrations. This works fairly well, but it is the most accurate for steady state oxidative metabolism. This means a steady state of exercise. So with indirect calorimetry, we kind of have an old school method and a new school method. So our older methods are very accurate, but they're incredibly slow. So if you look at this top picture here on your right hand side, this is called a Douglas bag. So quite literally what we used to do is we would strap big, almost weather balloon-like bags to somebody's back, and we would use a Hans Rudolph device to cover up their nose and their mouth and run some tubes behind them so they would breathe into a bag. And then as we would do physical activity, we would just change out the bags. You'd take the bag off, and then you'd measure the CO2 and O2 measurements in it. It worked, but it was slow, it was clunky, and it involved a lot of chemistry. Our newer methods, though, as you can see here on the lower right-hand side, are metabolic carts. The computer does all of the chemistry and the math for you. It's a lot less burden on the subject. You still get to wear the fancy face mask, but it's not nearly as bad. However, it is incredibly expensive, as in about $50,000 for a setup expensive. So while this is better than a full calorimetry room, we still have some costs involved. So looking more specifically at this metabolic cart, what we're going to do with this is we're going to measure the oxygen and the CO2 measurements. So you will hear these two terms over and over again for the rest of this course. The first one is VO2. This is the volume of oxygen consumed per minute, also known as the rate of oxygen consumption. And basically this is the volume of inspired oxygen minus the volume of expired oxygen. The next one is your VCO2. This is the volume of CO2 produced per minute, also known as the rate of CO2 production. And this will be the volume of expired CO2 minus the volume of inspired CO2. So using these two values, we create something called a respiratory exchange ratio. This will be really important for estimating what substrates we are using. So we know oxygen usage during metabolism is going to be dependent on the type of fuel we oxidize. This means that the more carbon atoms in a molecule, the more oxygen will be needed. So we know there is more oxygen needed to break down a fat than it is required for glucose or a sugar. From there, we create this respiratory exchange ratio, which is the ratio between the rates of CO2 production, oxygen usage. So your RER is your volume of CO2 divided by your volume of oxygen. So what this looks like in practice. The closer that your RER gets to 1, the more we're using glucose. The lower your RER gets, the more likely we're using fat. So in practice, you can see the math here. So looking up at glucose, it's going to require 6 oxygens plus 1 glucose molecule to produce 6 CO2, 6 waters, and 32 ATP. This means the volume of CO2 produced divided by the volume of O2 produced, 6 CO2 divided by 6 O2 gives us a ratio of 1. And then you do the math again for the fats. This gives us a ratio closer to 0.70. So basically this allows us to predict what substrate are we using, more fats or more carbohydrates. So this is a table comparing the percentage of calories from carbs and the percentage of calories from fats to the RER. So you can see at the top of the table, in an ideal situation where we're using exclusively fats, our RER would be 0.71. And then when we get to the ideal situation of 100% carbohydrates and 0% fats, we would be at a perfect 1.00. Realistically, we hang out somewhere between 0.76 and 0.8 at a resting state. When you start getting any lower than that or above 1, that means proteins usually are being used for energy sources. So, even though indirect calorimetry is kind of our best option for measurements during exercise, there are still limitations. This is because your CO2 production may not necessarily equal the CO2 that you're exhaling. You can have some caught up in the bloodstream, some that's left in the lungs, and some other areas. This also means that the RER is going to be inaccurate when we start oxidizing proteins. So as I said, you can get lower than 0.7, you have some proteins going on, or you're having issues with your equipment. If you get above 1, you're getting some protein breakdown. So having that RER near 1 may also be inaccurate because you have lactate buildup. This is going to increase your CO2 exhalation. Also, when you have gluconeogenesis, the production of new glucose, this is going to have an RER less than 0.7 again. So, another option to measure energy expenditure outside of this indirect calorimetry with the metabolic carts is we can use isotopes. So if you remember from chemistry, isotopes are elements that have an atypical atomic weight. So for example, you have carbon-14 is the most common carbon. So if we use carbon-13 or carbon-12, these are unique isotopes. It's still carbon, it just has a different weight. And therefore we can count this, and this gives us information. Our isotopes can be radioactive or non-radioactive. We tend to try to play with the non-radioactive ones in exercise physiology, but the cool thing is we can trace these throughout the body. So as I've mentioned before, we can use carbon-13, or we can use hydrogen-2, also known as deuterium. These are the most common isotopes, and this will create heavy water. So the H2 of the H2O is really 2 on the hydrogens as well. This allows us to study energy metabolism. It's really easy, it's super accurate, it's low risk, not too bad with the subjects. However, this is the most ideal for long-term measurements in terms of weeks and months. This is not a quick measurement technique. Additionally, getting these isotopes can be very expensive for labs, so it tends to only be used for high-level, grant-level research. All right, so shifting gears a little bit. How do we measure this energy expenditure at rest or during exercise? So we know the metabolic rate is going to be the rate of energy used by the body. And we're going to base this off of whole body oxygen consumption, and then we're going to try to correspond this to some sort of caloric equivalent. This means at rest, our RER, as we've previously discussed, hangs out around 0.8, and our VO2 is somewhere around 0.3 liters per minute. So we know at rest, our metabolic rate will be somewhere around 2,000 kilocalories a day. This is going to vary based off of body size, muscle mass, males versus females. That's typically, again, coming back to body size. But we know that there's just kind of some standards here. RER is going to be about 0.8, VO2 will be about 0.3 liters per minute, and calories will be around 2,000 kilocalories a day. So, looking more specifically at energy expenditure at rest, there will be a couple different things we need to pay attention to. The first being the basal metabolic rate. So our basal metabolic rate is the rate of energy expenditure at rest. This is quite literally, you're in a supine position, you're in a thermoneutral environment, you've just woken up after about 8 hours of sleep and 12 hours of fasting. I like to tell people that this is, you have woken up and then they attach the machine to you and then you're ready to go. This is incredibly restrictive in terms of the criteria to do it right, but it does give us information about the minimal energy requirement for living. So our basal metabolic rate can be impacted by a couple different things, most of it being your fat-free mass or your muscle mass. It can also be affected by things like your body surface area, your age, if you're under stress or duress, the hormones that you have circulating, and your resting body temperature. So, much less restrictive version of the basal metabolic rate is the resting metabolic rate. This will be fairly similar to your basal metabolic rate, usually somewhere between 5 and 10%, but it's much easier to do. The stringent standardized conditions are not required like what is required for the basal metabolic rate, and this gives us a range of somewhere between 1,200 and 2,400 calories a day to function. This one, on the other hand, I tell people is how much energy does your body need to sit on the couch and watch Netflix all day? So the next step up from that is your total daily metabolic activity. So this will include your resting metabolic rate, but then in addition, your normal daily activities. This can increase from your resting metabolic rate going from 1,200 to 2,400 kilocalories a day requirements to somewhere between 1,800 and 3,000 kilocalories a day. Competitive athletes, especially high-level endurance athletes, may consume upwards of 10,000 kilocalories per day and need to consume a lot more food than the average person. So, switching gears again, going from rest to submaximal aerobic exercise. So we know our metabolic rate will increase with exercise intensity. So why this works is we have the slow component of oxygen uptake kinetics. This means that at high power outputs, VO2 has to continue to increase to keep up. As I've increased my demand, I need to increase my oxygen consumption to keep up. This means that to get more energy usage, I have to bring in more type 2, which are much less efficient, muscle fibers. So this creates something called a VO2 drift. So what's going to happen is I have a maintained level of physical activity. We'll say it's something like 80% of my VO2 max. And what's going to happen is if I have to maintain that over a long period of time, we're going to see an upward drift due to some ventilatory and hormone changes. So that means, let's say I'm at 80% of my VO2 max and I'm running at, let's say, 7 miles per hour. That means if I want to maintain 7 miles per hour for long periods of time, maybe that was my 80% of my VO2 max, but now it's suddenly become 85, even though my intensity has not changed. That is a VO2 drift. Taking it the next level to maximal aerobic exercise. Our VO2 max is the maximal amount of oxygen that our body can uptake and use. This is the point where oxygen consumption cannot increase to counter a further increase in exercise intensity. This is our single best measurement of aerobic fitness. So if I want to know someone's aerobic abilities, I do a VO2 max test with them. However, VO2 maxes are not the best predictor of endurance performance. So just because you're fit does not necessarily mean that you're going to be an excellent endurance performer. We're going to see increases in VO2 max up to a certain point. Plateaus will occur somewhere between 8 and 12 weeks of training, but our performance can continue to improve. This is mostly due to improvements in exercise efficiency. Also, more training will allow an athlete to compete at a higher percentage of their VO2 max. So, talking a little bit more specifically about the maximal aerobic exercise, your VO2 max tends to be expressed in liters per minute. This is a very easy standardized unit, and we tend to use it when we're talking about non-weight-bearing activities, things like swimming and cycling. However, once I put body weight into the equation, so for example, I'm going for a walk or I'm going for a run, we then have to take the VO2 max and normalize it for body weight. It is then converted to milliliters per kilogram per minute, mLs per kg per minute. This is because we need to have a point of comparison for individuals of different body sizes. So is it more impressive to have somebody with a VO2 of 50 mLs per kg per minute that weighs 300 pounds, or someone who weighs 150 pounds? I'd be more impressed with a 300 pounder. All right. So we also know that untrained individuals are going to have lower VO2 maxes than trained individuals. So if you look at your graph to the side, we can see two different individuals, the trained in blue and the untrained in red, performing a VO2 max test. As you can notice, the untrained individual did not get as far as the trained individual. That makes sense. Also, we see some differences in VO2 max between men and women. However, this is not due to the capability of men and women. It's mostly due to the body size differences. Also, women have a lower fat-free mass and hemoglobin volume than men, so it's just much more difficult to have high VO2 max numbers. So, to shift gears again, let's talk about maximal anaerobic exercise. So we know kind of from our conversations up until this point that no activity is going to be 100% aerobic or anaerobic. This means that we have to kind of estimate the anaerobic contribution. Typically, the two ways we do this is we look at something called excess post-exercise oxygen consumption, or EPOC, and lactate threshold. So let's look at EPOC first. When we participate in physical activity, there's going to be an initial increase in oxygen demand that cannot be kept up with the oxygen consumed early in exercise. So we're going to burn through more oxygen than what we have available. That's okay, because our body makes up with this with our anaerobic pathways. However, this is going to incur an oxygen deficit, as we can see in the chart here to the right. So early on in exercise, we're burning through more oxygen than what we can supply. So we're going to go into a deficit. However, once we have completed our physical activity, we are going to make up for that. We know that our O2 consumed post-exercise is going to be greater than the oxygen demand of early recovery. This is excess post-exercise oxygen consumption, or EPOC. Basically, over-consuming oxygen after you've finished activity is going to help us replenish our ATP PCR stores. It'll help us convert lactate back to glycogen in the liver. It will replenish our hemoglobin and myoglobin of oxygen, and it will clear any excess CO2. This is why when you finish exercise, like I've gone for a run and then I stop running, you don't just magically stop breathing heavy. Your body has to take some time to replenish the oxygen. So EPOC means we're going to have an increased demand early, so we'll consume more later. Our next concept here with anaerobic energy expenditure is a lactate threshold. So if you remember when I said VO2 max is a great predictor of aerobic fitness, but not aerobic performance, that is because lactate threshold is our big predictor of performance. So your lactate threshold is the point where blood lactate was going to start accumulate and hence going to increase at a marked rate. That's because lactate production is going to be greater than lactate clearance. This means we don't have enough oxygen available to take the pyruvate and put it through the Krebs cycle. So my pyruvate gets converted to lactate. We can kind of keep up with production and clearance to a certain point, and then we're going to get this accumulation. This is going to show us the interaction between the efficiency of our aerobic and our anaerobic systems. This is why the lactate threshold is our best predictor of potential endurance performance exercise. Our lactate threshold typically is going to be presented somewhere as a percentage of our VO2 max. So, what does this mean? That means the higher your lactate threshold, the better endurance performance you're going to have. So, what this means realistically for coaches and athletes, if you have two athletes with the exact same VO2 max, the one with the higher lactate threshold is typically going to be your better performer. So, the next thing we want to talk about is how do we actually measure somebody's anaerobic capacity? Unfortunately, when we're talking about anaerobic capacity, there's no magical test like we do for aerobic, which is the VO2 max test. So we have some imperfect but accepted methods that we tend to use. The first being the maximal accumulated oxygen deficit, so relating back to EPOC. We have something called the Wingate anaerobic performance test and our critical power test. Both the Wingate anaerobic test and the critical power test, we don't have a Wingate bike at our lab, and that is a blessing because they both suck. People get very nauseous, people vomit while doing these. I've had to do both of them in my studies. I don't recommend it for anybody. So, the next concept past aerobic and anaerobic performance is our economy of effort, so our exercise efficiency. So as athletes become more skilled, they're going to use less energy at a given pace. So this means even if somebody has trained to their maximal VO2, they can still get better at their sport, or their performance can still improve, just because they get better at doing the thing. This is going to be true independent of VO2 max, and this is just because the body learns to become more efficient and have better energy economy with practice. We also have kind of this multifactorial phenomenon going on. We know that economy increases with the distance of the race, so individuals that run a marathon are much more efficient runners than people that run the 800. We also know that practice leads to better economy of movement. Your form improves. Also, this is going to vary with different types of exercise. So somebody that's a very efficient runner, that does not mean they're going to be an efficient swimmer. So what efficiency looks like for an individual will vary between the events, as well as what does efficiency look like between the events independent of that individual. So, all of that is to say, if we were to build the perfect successful endurance athlete, this individual would have a very high VO2 max, they would have a high lactate threshold, expressed as a percentage of their VO2 max, they would have a high economy of effort, they would be super efficient at whatever they were doing, and they would have a high percentage of type 1 muscle fibers. You remember these are the ones with lots of mitochondria and are able to produce a lot of ATP for us. So there are some things with this perfect endurance athlete we can change with training, and there's some things we cannot. So first, that very high VO2 max. I can train somebody to have a higher VO2 max, but there is an upper limit of potential based on your genetics. So there is a genetic ceiling here. It does not matter how much I train you, I can't take you past your genetic ceiling. Additionally, with lactate threshold and economy of effort, the more you practice and the better you train, the more this improves. This is something I can physically change with training. And then finally, the percentage of your type 1 muscle fibers, that's another genetic component. I can't change that once it's there. So if you remember from our earlier discussion, I can take a type 2 muscle fiber and try to make it more endurance-based, but that's still a type 2 muscle fiber. it's not going to fully convert between the two. I just basically have a type 2 muscle fiber with some more endurance. So, things to think about with performance. So, switching gears again, we need to also look at the energy cost of various activities. This is because various activities are going to vary with their cost from type and intensity of that activity. So, we calculate this from our VO2 and express it in kilocalories per minute. So this means that typically to run a mile, we say it costs around 200 calories. However, but when we use these values, it completely ignores any anaerobic components or our EPOC. So when we start to think about daily expenditures, this is going to be dependent on our activity levels, and then just some other inherent body factors like age, sex, size, weight, and fat-free mass. So now is the kind of part 2 of chapter 5, which deals with the aftermath of training, mostly dealing with fatigue and muscle soreness. So fatigue has 2 different definitions. The first one is fatigue is a detriment in muscular performance with continued effort accompanied by sensations of tiredness. So literally you exercise until you're tired. The second part of fatigue, though, is the inability to maintain the required power output to continue the muscular work at the given intensity. So you have the sensation of being tired, which is fatigue, and then you have the failure of your physiology, which is fatigue. But in both of these instances, if you rest, it reverses itself. So, basic working understanding of fatigue. So, even though we have a basic understanding of what fatigue is, it is incredibly complex. Fatigue is going to vary via the type of exercise, the intensity of the exercise. What muscle fiber am I asking my body to use? What is my training status? Did I adequately fuel myself? Am I hydrated? Did I sleep enough? Fatigue has a lot of different factors to kind of change its results. But we've kind of identified 4 major causes that may be synergistic and interact with themselves, or maybe not. The first one is inadequate energy delivery or metabolism. The second is the accumulation of metabolic byproducts. The third is the failure of the muscle contractile mechanism. And the fourth is altered neural control of our muscular contraction. So let's dive into each of those a little bit more. So let's talk about the failure of the energy systems first. So specifically PCR depletion. So we know that the depletion of phosphocreatine is going to coincide with fatigue. We know PCR is used for short-term high-intensity effort. If we remember, it's somewhere around 5 and 15 seconds. And we know that PCR is going to deplete much more quickly than our total ATP stores are going to be. That means we are going to have an accumulation of phosphates, which could be causing issues with our energy system. Also, pacing is going to help defer PCR depletion. So I know everybody has done this before. They've been asked to run a sprint and then they go out way too hard and you burn out at the end. That would be an example of fatigue. If you pace yourself appropriately, it's not as bad. So the next concern is glycogen depletion. So we know glycogen is the storage carbohydrate in our muscles and our liver. Glycogen reserves, however, are going to be limited and we can deplete them relatively quickly. And then this depletion tends to correlate with fatigue. This is going to be related to the total glycogen depletion, not the rate of glycogen depletion. I can deplete glycogen slowly, or I can deplete glycogen rapidly. It's still going to relate in fatigue. Typically, we deplete glycogen with higher intensity activity much faster, and typically we will see glycogen be depleted much faster in the first few minutes of exercise. So, if you look at this example here, the graph to your left is going to show the decline of glycogen in the gastrocnemius, or the calf muscle, during 3 hours of treadmill running at 70% of VO2 max. So we can see as they are continuing on with their activity, glycogen stores are dropping. The second graph on the right is going to show this individual's perceived effort. So during this 3-hour treadmill run, he rated his effort as moderate for almost an hour and a half. But as that glycogen started to decrease, to a certain point, he started to say he was more fatigued than he did initially. So, furthermore, on the glycogen depletion, our fiber type and our recruitment patterns matter. So fibers that are recruited first, or most often, are going to get depleted the fastest. This means our type 1 muscle fibers are going to deplete after moderate endurance activity. Also, the recruitment dependent on the exercise intensity. If we have light or moderate intensity exercise, we tend to pull glycogen from our type 1 muscle fibers. If we're playing with moderate to high intensity, it tends to be our type 2A, and then maximal intensity tends to be type 2X. So this is what this looks like visually. So this first picture is going to be a micrograph of muscle fibers that have been taken from a runner after a 30-kilometer run. So in this picture, it's been stained so you can see the differences between the type 1 and the type 2 muscle fibers. So in this particular picture, the type 1 muscle fibers are going to be that deep dark red color, and your type 2 or fast twitch muscle fibers are going to be kind of that whitish pink color. So keep this in mind. Looking at the next picture, this has been stained to show glycogen. So you notice here, same runner, same 30-kilometer run, but you can see that there is still glycogen in the type 2 muscle fibers and almost no glycogen in the type 1 muscle fibers. This makes sense. A 30-kilometer run, which is about 18.5 miles, I'm using pretty much exclusively type 1 muscle fibers. They've been used over and over again. Fast twitch hasn't had to come into play. Where's the glycogen going to leave? It's going to leave from type 1 first. So, also we know the depletion in different muscle groups is going to be based on how I use them. So activity-specific muscles will be depleted the fastest, and they will be recruited earliest and longest. So depleting this with blood glucose, we know muscle glycogen will be insufficient for prolonged exercise. That means I got to pull glucose from somewhere. This tends to be from my liver glycogen, which converts to glucose into the bloodstream. However, as our muscle glycogen declines, our liver glycogenolysis is going to go up. We're breaking down glycogen in the liver. If we have muscle glycogen depletion plus hypoglycemia, so low blood sugar, we're going to have fatigue. So we have to maintain a certain rate of muscle glycogenolysis, so muscle breakdown of glycogen, to maintain our NADH production in the Krebs cycle and our electron transport chain activity for phosphorylation. So if we have no glycogen, we're going to have inhibited substrate oxidation. The best way to remember this that I've heard in graduate school was that fat burns in a carbohydrate flame. If there's no carbohydrates, I don't care how much fat you have available to you for oxidation, you can't turn the Krebs wheel. So if there's no glycogen, there's no glucose, you're fatigued, you're out. So when we have glycogen depletion, our free fatty acid metabolism is going to increase. But if it's too slow, we can't supply sufficient ATP for the given intensity, and we burn out. So our next cause is metabolic byproducts. So there are 4 main byproducts we're concerned about and its relationship to fatigue. The first is the phosphates that are kind of floating around from the rapid breakdown of PCR and ATP. If I can't pull them in with ATPase, then I'm having problems. I just have waste products floating around. The next is heat. The body retains heat and our core temperature increases. This is going to decrease the efficiency of enzymes. We start to overheat. You can get heat stroke, heat exhaustion. This is going to cause problems. The next is lactic acid buildup. This is our byproduct of anaerobic glycolysis. If we cannot shuttle lactate out of the way to be used efficiently, this can cause some problems with oxidative glycolysis. And then the hydrogen ions from lactic acid convert to lactate plus a hydrogen ion. Now I'm changing the pH of the metabolic tissues, start to denature enzymes. We have some problems. So we know heat alters metabolic rate, so it will increase the rate of carbohydrate utilization, which means we're going to go through more of glycogen depletion faster, and high muscle temperatures impair muscle function. So it helps to a point, and then it starts to go the other way. Also, we know that heat is going to impact our time to fatigue. So if we look at ambient temperature, we know our time to exhaustion is the longest at around 11 degrees Celsius. Our time to exhaustion is the shortest at around 31 degrees Celsius. However, we can kind of trick this a little bit if we do some muscle pre-cooling before we go into this intense heat. That's great for long-term exercise, but if you think about it, if you want to like ice your hamstrings before you go running in the heat, you may pull a hamstring. So that's always been an interesting thought to me. Next, looking at these metabolic byproducts, if we look at lactic acid, this will accumulate during brief high-intensity exercise. If we cannot clear it, it will convert to lactate plus a hydrogen ion. With all of these hydrogen ions accumulating, this is going to decrease muscle pH. This causes an acidosis. We have some buffers in our muscle and our blood to try to minimize this, but sometimes that's not enough. So our buffers can minimize the drop in pH from 7.1 to about 6.5, but it's not going to do much after that. Cells, therefore, can survive, but they don't function well. If our muscle pH gets below 6.9, this is going to completely inhibit glycolytic enzymes and ATP synthesis. If pH equals 6.4, there will be no more glycogen breakdown. So if we don't have enough oxygen to run the Krebs cycle, we're just going to build up these hydrogen ions and everything's going to shut down. The next cause of fatigue is neurotransmission fatigue. This is when we have a failure at the neuromuscular junction that prevents muscular activation. This could be reduced acetylcholine synthesis and release. It could be altered acetylcholine breakdown in the synapse. It could be an increase in muscle fiber stimulus threshold, or it could be altered muscle resting membrane potential. Additionally, fatigue may inhibit calcium ion release from the sarcoplasmic reticulum. So there's a lot of different things that could be going on the neural side. You can also have central nervous system fatigue. We know it probably plays a role in fatigue, but we don't know quite how this works yet. This is also because fiber recruitment has a conscious aspect. When I am in the discomfort of exertion, I can mentally push myself through that and keep going, or people tend to back off. So that stress from exhaustive exercise may be too much and people quit before they're truly fully fatigued. Person may be subconsciously or consciously unwilling to endure pain. The discomfort of fatigue typically is a warning sign that you're pushing your body too hard. However, when you are an elite athlete, you learn proper pacing and you tend to tolerate fatigue better. I had a track coach once that told me to embrace the suck. It is a good way to think of mentally being able to overcome certain aspects of fatigue. So this is a graphical example of that concept. So this is going to show the relationship between power output in watts and the time that power output can be maintained. So our critical power is defined as the relationship between these two. So the maximal power output that can be sustained without fatigue, limiting the duration of performance. So there is a link between energy expenditure and fatigue. So this is the tolerable duration of high intensity exercise. Our highest metabolic rate maintained entirely by our oxidative metabolism. This tends to increase with endurance and high intensity training, but this also can decrease with age, chronic disease, and hypoxia or low oxygen levels. We can also correlate this with performance in events anywhere between 2 minutes and 2 hours. So we have a pretty strong relationship here. So, last topic to discuss is going to be muscle soreness and cramps. So general muscle soreness tends to result from exhaustive or high intensity exercise, especially if it's your first time going at that intensity or doing that particular exercise. Muscle soreness can be felt at any time. You can have more acute soreness during or immediately after exercise, or you can have delayed onset muscle soreness, or DOMS, 1 or 2 days later. So looking at acute muscle soreness, this tends to be felt during or immediately following a strenuous or novel exercise. This typically is related to the accumulation of metabolic byproducts. You also tend to have some tissue edema where plasma fluid gets into the interstitial space, and this is going to cause acute muscle swelling. This is not comfortable. It puts pressure on your nerve receptors, which gives pain responses, but acute muscle soreness tends to be gone sometime in a few minutes to a couple hours after the activity. On the other hand, DOMS, or delayed onset muscle soreness, tends to appear 1 or 2 days after that exercise bout. I didn't know what this was called when I was in high school, so I just always used to call it 2-day sore, because you would exercise and then 2 days later you were sore, and I was like, yeah, that workout was 2 days sore hard. Now I know that's DOMS. But DOMS can range anywhere from stiffness to severe restrictive pain. And this is mostly due to eccentric muscle contractions that are occurring during bouts of activity. A good example of this is the pain you feel when you run on level ground versus the pain you feel after you've done downhill sprints. Our DOMS is not caused by an increase in blood lactate concentrations. This is true muscle damage. So this means that structural damage has occurred, and this is because we can tell that there are muscle enzymes in the blood, things like myoglobin. So these concentrations can be anywhere from 2 to 10 times higher than what we would expect normally after a very heavy training. And the onset of DOMS tends to parallel the onset of this increase in muscle enzymes in the blood. We're actually causing damage to the sarcomere Z discs that are our anchor points. So this means that this muscle damage has actually occurred. However, muscle damage is going to precipitate muscle hypertrophy. So if I want my muscles to grow, I actually have to damage them so they can repair themselves and come back stronger. So we actually need this to occur for muscle hypertrophy. DOMS also tends to be accompanied by inflammation, and this inflammation tends to lead to soreness. This is because white blood cells, that their job is to defend the body against foreign materials, are going to flood to the area of muscle damage, and this will increase with soreness. Also, we have some other substances that are going to initiate this inflammation response. So our damaged muscle cells are going to attract neutrophils, which are specialized white blood cells. These neutrophils will then release an attractant chemical and some radicals, and then these will stimulate pain receptors. We also have macrophages that are going to go in and remove any cell debris. So the specific sequence of event for DOMS. First, you're going to have high tension in the muscle, which is going to create some sort of structural damage to that particular muscle. That membrane damage will then disturb the calcium ion homeostasis, which is going to inhibit cellular respiration and activate enzymes that degrade our Z discs. From there, after a few hours, we're going to see an increase in circulating neutrophils. Also, we'll have products of macrophage activity and intracellular contents accumulate. So you'll have histamine, which is an inflammation response, kinins, potassium ions. All of this is going to really irritate your free nerve endings, so you'll feel uncomfortable. And since we know eccentric exercise tends to be the cause, it tends to hurt worse with eccentric exercise. Also, our fluid and electrolytes are going to kind of shift into the area, creating localized swelling. So DOMS, when you're actively going through it, is going to reduce your muscle force generation. This means while you are repairing the tissues from DOMS, you're going to have a loss of strength from the physical disruption of the muscle, the failure of your excitation-contraction coupling, and the loss of contractile protein strength. So, the good news is, though, once it is repaired, it comes back stronger. But while you're going through it, you're going to be weaker. So how do we minimize DOMS? We need to reduce DOMS for effective training. It's okay to be a little sore after exercise. It's not okay to be debilitated. So the 3 best strategies to reducing DOMS are to minimize eccentric work early on in your training cycle, to start with a low intensity and then increase gradually so you don't overdo things, and then start with a high intensity exhaustive training. So soreness is bad at first, but it's much less later on. And the last thing I want to talk about are muscle cramps. So we have 2 different types of muscle cramps. The first is exercise-associated muscle cramps, or EAMCs. This is going to be localized to an overworked muscle. It's caused by a lack of conditioning, improper training, and depletion of those particular muscles' energy stores. I can also induce this by electrical stimulation. So if you've ever played with a stem machine before and the athletic trainer or your buddy has cranked it all the way up, I can create a contraction and hold it for long periods of time. Typically, when you have a muscle cramp due to exercise, you just treat it with stretching, and then you'll have a reduction when you change the excitatory properties of that motor neuron. And then the last type of muscle cramps are heat cramps. This is going to be associated with large sweat and electrolyte losses, especially sodium and chloride. This tends to also hang out with dehydration. So how do we treat that? High sodium solutions, ice, massage, stay hydrated, try to not exercise in heat. Whew, that was a long one. So that is the end of Unit 1, and I look forward to seeing you guys again for Unit 2, starting with Chapter 6.